Continuing on with class 20, here's example 1, or 6.1, from Borgnacki, where you have a Carnot cycle heat pump using refrigerant R134A as the working fluid, and the heat is absorbed into the fluid at 0 degrees Celsius, during which the process changes from a two-phase state to a saturated vapor. The heat is rejected at 60 degrees Celsius and ends up as a saturated liquid. We want to find the pressure after the compression and before the heat rejection process, and determine the coefficient of performance for this cycle. I'd also maybe want to try to find the other states. I might want to find the quality right here. We could find the other parameters if we find this quality. But what we're doing here is we're absorbing heat between points 4 and 1. And then we're compressing it to go from 1 to 2. We're extracting the heat from 3 to 4. Is that, yes? And then this is where we're like expanding right down to here. So like is that true? We're dropping down in pressure, so I think so right here. So let's take a look back at a figure that describes our process. That can also often be a useful thing. So here is an example. This was 5.5, where we had this. So we were coming from, and I have my pages marked here, so I'm taking my pencil out. So as I try to shuffle this around. So we're starting at 1 right here, all right? So we went from 4 to 1, and this is where we took out, wait a minute, is this the air conditioner or the heat pump? Is the cooling a room. So this is not the heat pump. I'm sorry, I apologize. So that was stupid. Let me see. This is the air conditioner. So are we still going from 1 to 2? We're just putting this thing backwards right here. So this is actually in the house, and this is actually outside. So we're still doing the same thing here. We just need to reverse which way we're looking at it. Like pretend this is the outside air and this is in the house, and we'd be numbering it the same way. So we are compressing it, and then we are throwing heat into the house. We come back out here, we expand, and then we take in this low heat, right? The low temperature heat coming into there, and then we're compressing it, and we go through the cycle again. So let's take a look at how that looks again on here, right? We're starting right here where we're compressing the thing up, and then we are taking heat from the outside. Is that true? No. We are compressing it out. We are letting heat come outwards. Yes, come out into the room, and then we are expanding it. So this is we're actually condensing this. So here's the condensing portion of this, and then we drop down here into this mixture, right? So we went from a fluid back into a mixture right here, and then we absorb heat from the outside world into here, right? So we're going from this low temperature to this high temperature right in there. So what they're asking for is to find the pressure right here. So let's start from where we know something is true. And so let's start from state 1. And by the way, this is similar but different to your homework problem 1 in homework 9. Similar but different. So we're going to go to the table B.5.1, which is the saturated condition for this refrigerant. And we'll look at the temperature equal to 0 degrees Celsius. And while we're there, let's find the saturation pressure, because that's going to be the same pressure all the way along here, right? So the pressure and the temperature remain the same as it's in the vapor state. So that saturated pressure is going to be 294 kilopascals. Actually, I have the book open, so let me take a look at there. We're also, while we're looking here, note that we are at the gaseous state right here. It just says that it goes from, it absorbs heat during the process. It changes from a two-phase, which is right there, to a saturated vapor, which is right there. So that's, we know this thing is at 0 degrees, it's a saturated, so we can find that point. And we probably want to find what the entropy is, and that's going to be the entropy of the gas at this temperature. So let's take a look here, and this is table B51. Here's the entropy, and here is 0 degrees. And if we take a look across here, we see that we have a SG, so the gaseous entropy, 1.7262. Notably, we are at 294 kilopascals. So we found the information we need for that. Right, so we already wrote that down, and there was a 0 right there I missed. And then this was the G at that spot, so 1.7262. So if our goal is to find the pressure right here, right there, there's the PV diagram, and here's the TS diagram. We have one of the coordinates for this. We have this guy right here, and we also have this temperature right here. So we can use those two things to find what the what that pressure is going to be. So let's go to, we can either go to state, let's go to states 2, and let's go to state 3. State 3. And so we're still in this table, but we're going to go to 6 degrees. And we know that one right here is going to be for the fluid. But we don't necessarily, they're not really asking us for that, right? They're going to say they want to know, find the pressure after the compression, which is going to be that right there. It should be the same, well, it's going to be, okay, well, we're going to find, okay, so we're going to find what the pressure is right here. So let's go to PSAT. Go to 60 degrees. So 60 degrees, it's going to be 1,681.8. 1,681.8 kPa. And the just looking right there, okay, so we could find that the SG, okay, 1 second. Okay, so I don't necessarily need to know that, but I do want to know something else later. So let's go ahead and write this down. So that's going to be a gaseous at state 3 of 1.2857. Not gaseous, fluid. 1.2857. Kilojoules per kilogram degree Kelvin. Now let's go to, well, let's just check state 2. All right, so we're going to go at, well, this is the same thing. So this is still right here. We have all of that. We also have that the SG. So we're just going to check the SG right here. And we kind of probably know it to be true, so I don't even know if this is pointless. 1.7040. 1.740. Right? So we know that the at state 2, we are actually going to be superheated, right? Because this is that spot right there. right? It's right here at that spot. So what we need to do is we're going to be isentropic from 1 to 2. So this is we're going to need to be on the lookout. Where can we find 1.626? 1.7262, sorry, in the superheated tables. So now we go to table B.5.2, and we look up, we're on the lookout for this right here at 60 degrees, right? So at T is equal to 60 degrees Celsius, but there's going to be different pressures. So we're going to go at P, we're going to find it. We go 1.726 at 60 degrees. So I started out with 500 kPa, just randomly, I just happened to pick there. And we see that we're 1.8560. So that's no good. By the way, we should maybe also have a clue that the saturation is 1.681. So we're going to be in that vicinity somewhere, right? But we're going to probably have a lower pressure than that because that's the saturation pressure. But we need to have superheated steam, so it's going to be a lower pressure than this. We might want to just jump ahead and go to somewhere near 1600. So let's look at 1200, 60 degrees, we get 1.7584. Remember, we want 1.7262. So, we go down to 14. We're right there. We're getting lower. We're dropping down right here. So we're getting closer. We go to 1600 and we get 1.7135. So we're in between 1600 and 1400. So let's record down what these are. So we're in 1400 kilopascal, and at P is equal to 1600 kilopascal. We will get an S of equal to 1.7360. And probably taking time to write that thing out every time. And then at 1600, we have 1.7135. So we want to go ahead and take and interpolate. So we'll take 1.7360, 1.7135, and this is at 1400, and here's at 1600. And we were taking this right here, isentropic, going vertically from here to there, 1.7262, and there's the thing we want to find. So I won't bother going through this interpolation again, but I did do it. 1487 kilopascals. So that answers one of the questions. In fact, I think right here we've already answered one of the other two questions, right? Because they said find the pressure after compression and before the heat rejection process, which I guess is this process right here. So this is what we wanted to find. So we were able to find that it's actually going to be 1,487 kilopascals, which you could see on a PV diagram. Yes, this is less right here than this 1682, which is what we found was going to be the PSAT right there. They asked for the coefficient of performance. We could do that. We could have done that without any of this because they gave us the temperature, and if it's a Carnot cycle, we know that the coefficient of performance for a heat pump is going to be TH over TH minus TL, right there. So that ends up being, this is 60 degrees plus 273 divided by, and then you could just use, because they're subtracted from each other. You don't need the 273 in both of these, but we can do it anyway. 0 plus 273 minus, I said 60 plus 273 minus 0 plus 273. And you end up with 5.55. And of course, this is a good thing to know because that's the best we can do for this heat pump given these two temperatures that we're trying to go between. One thing I would add is added value, just something that you might want to look through, is to find what the quality of this was going to be. We could go back to the data that we had for the 0 degrees right here and get the SF right here, or we didn't really, yes, we need the SF and then the SFG in between there. So at t equals 0 degrees, and this is, I guess we'll go back to the table B 0.5.1. We have the SF is equal to, no, we gotta go to the next one. At 0 degrees, we have 1, and we have 0.7262. So let's go 1, and SFG is 0.7262. And so when we're looking for the quality here, we're going to take S is equal to SF plus X, SFG, right here. And we know it's an isentropic process from here. So at 3, we collected this guy. So 1.2857 is equal to 1 plus X, and I guess this is going to be 4, X4, times 0.7262. And X4 is going to be 1.2857, subtract 1 out, and divide by 0.7262. And you end up with 39.34%. So that's something worth knowing. We can also, from this, I think we have all the things that we would need to know, and these are all reversible processes. So we could go ahead and use the entropy with the Q to find the different values, right? So I don't know, we're in 18 minutes and I have a meeting in 6 minutes. Do I want to do that? I think I could find QH, which is going to be TH times, in this case, S2 minus S3, right? But we have to make this, this TH is going to be, the high temperature is going to be in Kelvin, so we go 333 in Kelvin times 2 minus 3, right? So 2 we established was 1.7262, and we subtract out 3, which is going to be this guy right here, right? This, like here is, yeah, so here is, so 1.2857. 1.2857, and so 1.7262, boom, and 1.2857 minus, and then 333, boom, and so we should get 1 146.7 kilojoules right there, right, is being placed into this. And pause. Okay, so what I should have done, I forgot to do, is while I was collecting this other data, I should have collected what, in order to get what the work was going to be coming in between each of these processes. Yeah, I should have gone and collected all the U's, right? Because we're pretending like these each of these processes is a closed system. So recall that Q, and this should be a small q, by the way. Remember that delta U is going to be equal to delta Q minus delta W. And we have isentropic processes that take place during this portion right here. But we need the network that's taking place right here. So we have to find out what all these Q's, these W's are going to be that's coming in. So we have work going in through right here. But I also have to recognize that we're going between here and to there. Yeah. So what we want to try to do for that is find what we end up having. The delta U's are going to be the delta works that take a place around the whole thing. So as we are going around the cycle, each separate point we would find what the work is, either positive or negative, based on what the change in internal energy is going to be. Well, specifically we would use this right here with the Q's for this process and this process. But we would also find out what the net work was going to be based on this same equation, this guy right here, but taking into account what the delta Q's were going to be. So that's what homework 1 is like, or how it's similar. But it's not part of this example in the book right here. But we would find what the QH is going to be. So in between, so this is going to be between 2 and 3. That we also do the same thing here between 4 and 1, right? Whether it was positive or negative depends on the direction of the thing. And then, and this should have been a negative right here, right? So that should have been 3 minus 2, and that should have been a negative value. And then compare it with right here. So I'll probably, maybe I'll make another example to try to help with this homework. Yeah, I think I might do that. So anyway, let me think about that. All right, so this is the end of the of this example right here. So we accomplished our example right here where we got our coefficient of performance, and we got the 2 pressures that we cared about right there. Well, actually, I don't think they asked for that. They asked for this. So I'll go into the next example and then consider making another one after my meeting.